Hello everyone. I would like to thank everyone for attending this virtual session of Furnaces North America 2020, and we're going to be discussing the keys to managing and controlling distortion in heat treating. Distortion is a major issue in heat treating. There was a previous study in Germany in 2005 that indicated that the cost of distortion in Germany alone was in excess of €1 billion. Distortion can take many forms. It can be from volume changes, such as from phase transformation, like the coupled phase transformation of martensite, or it can be from precipitation reactions occurring. It can also be elastic plastic deformation from transformational stresses, thermal stresses, or elastic stresses from just residual stresses. As I indicated previously, distortion is always a problem in all heat-treated processes. It doesn't matter whether it is aluminum or steel or superalloys. It is always a problem. Now, typically, it's most severe in carburizing and hardening of steels, particularly for gear distortion. And this is because of the different martensite start temperatures between the core and the case, which can be very significant. For instance, in the core, it could be on the order of 450 degrees, 500 degrees Fahrenheit, where in the case that can be 200 degrees Fahrenheit. This can cause problems, particularly in thin sections. The inside will transform first, and then the core. Now, you typically have two types of distortion. You have a body distortion, which is an outer roundness, or you can have distortion of the tooth distortion, of the tooth geometry. The body distortion also strongly influences the gear tooth geometry. Now, there are really two sources of the heat treat distortion, particularly in steels and also in aluminum. There's the transformational stresses, and it's coupled with the cooling rate, and it's coupled with the thermal stress. This is particularly true in steels. The transformational stress, for instance, the expansion of martensite, is on the order of 3%. Thermal stresses, these are just stresses due to differential in heat transfer from center to surface and from surface to surface. The heat transfer, which is the heat stresses and strains and phase transformation, contribute to distortion in gears. Thermal stress is surface to surface thermal gradients. And it can also be center to surface thermal gradients. Thinner sections, such as gear teeth, will cool faster than the thicker body. I can have the interior cooling much slower than the exterior of the body. Now, alloying elements with different densities also experience different specific heat volumes. All right, this can also cause issues with distortion. Now, these internal stresses cause extensive deformation as a gear cools. With the faster the gradient, the faster the quench, the greater the thermal gradient. The greater the thermal gradient, the greater the amount of residual stress that will be produced just from thermal stress. For instance, you will see the elastic and plastic strains are sufficient enough that can cause cracking. For instance, in aluminum alloy, you will see large deformations in a steel part. You can have excessive distortion from teeth. The teeth will become distorted, can become either have greater runout, etc. A second form of stress is transformational stresses. And these are the coupled stresses due to phase transformation. A very common one is the volume expansion due to martensite formation, which is typically can be up to 3%, which is extensive. This happens first that as I heat it, up to my austenizing temperature, I'll get a volume increase from thermal expansion. I then get a volume decrease as the ferrite transforms to austenite. Okay, it switches different from a which is the crystal structure. Then my volume will increase again due to the thermal expansion, with the difference being the volumetric expansion between austenite and ferrite. This is also one reason why you may want to preheat, particularly in tool steels or any very intricate part, is to allow those thermal gradients to settle in and not cause any differential strains, because one part is heating up faster than another part. Now, when I quench the part, I get a volumetric expansion as it cools. I then get austenite transformation to martensite, which is a volume expansion up to 3%. Typically, the outer fibers will transform first, then the inner fibers. Now, this can be different if it's a carburized part, where my inner fibers will transform first and then the outer fiber. This can also contribute to a stress reversal. In fact, you can see the stress reversal in the pictures to the right, where I'm quenching a sword. This sword is produced in a fashion typical to Japanese swords. In fact, you can see that the sword will deflect in one direction, and then when phase transformation, it produces the characteristic bow of the katana, or the Japanese sword. In this illustration, I am showing the difference of two different alloys, ostensibly same carbon content but different alloy, between a 5120 and a 4120 SAE steel. Okay, I will see both as I'm heating up. I will see a variation of the helix angle before carburizing and then before quenching. It's predominantly a volume expansion. Then during quenching, I will see a change in the helix angle, and then I'll see the difference between one forming a bainite and the other one forming a martensite transformation. And you can actually literally see the phase transformation between the teeth, the helix angle varying back and forth in the stress reversal. And then finally we see the 5120 with a smaller variation helix angle than the 4120. And this difference is just due to the alloying content and the formation of the different structures, bainite and martensite, within the steels. In most manufacturing operation, the raw material comes in a variety of different shapes. It could be plate, it could be rod, it could be sheet. All right, then it is initially shaped using some sort of forming operation, a forging operation. Then once that initial shape, it can be put into a closer net shape of, through some sort of machining operation, even shearing. For instance, you could be hobbing it, you could be milling it, you could be turning it, broaching it, some sort of machining operation. Then as I go into the heat treat operation, I will heat it up to the austenize, I'll carburize it, I'll quench it, and then I'll temper. And then finally, after a heat treatment operation, I will then do other operations to it. I may straighten it, I may have some hone if it's may hone it. If it's a large bore, there may be grinding on the teeth. I may be plating it, or I may paint it, or I could be doing all of these. Each of those operations that I indicated previously, whether it was the incoming material, the shaping, machining, heat treating, or the finish operations, contributes in some fashion to the distortion and residual stress of the part. I have to look at, for instance, the incoming material. What is the prior condition in microstructure? Is there decarburization present? What is the alloy? All of that will contribute to the amount of distortion. I can also have how the part is designed. What is the part geometry? For instance, in landing gear, it's notorious for having very thick sections attached to very thin sections with very long bores. I mean, it's just asking to be distorted. How the steel is procured. Is it actually the steel that you say it is, or did procurement get something cheaper? What is the alloy chosen? As a general rule, the more alloying that you put into it, typically the more alloying that you put into it, the greater the chance of distortion. Then there's all the stresses that go into prior to heat treatment. It's the cold work from forming and stamping. It's the forging stresses. It's the machining stresses, grinding stresses, any shot plating, shot peening that you're doing. It's also any plating that you're doing, for instance, applying copper for decarburization control. Heat treating can also contribute to, for instance, are you non-uniform heating the part? For instance, if you heat the part up very rapidly, the very thin parts will contribute to heat up very fast than the body of the part. Are you preheating? That can reduce the amount of distortion by allowing the thin parts and the thick parts to heat up at the same rate. For instance, the load density is the entire load being heat treated uniformly. You can also have part-to-part interactions, banging onto each other, carburizing, atmosphere control. All these things contribute to distortion and residual stresses. And we haven't even talked about quenching yet. Now, when we talk about quenching, the biggest factors are the quenching temperature, or the quench bath temperature, the amount of agitation and the uniformity of that agitation, the type of quenching, whether it's an oil or a polymer. Racking can play an extremely important role, whether it is to make sure that the parts are seeing a uniform heat transfer along all the surfaces. It depends on whether the parts are hanging upside down, right side up, or sideways. Can make a big difference in the amount of distortion that these see, and that's due to non-uniformity of heat transfer. You can also see part-to-part interactions. So for instance, I had a customer that had a quench tank, and he was quenching clutch plates. And when he was racking these parts very nicely, perpendicular to the motion of the integral quench. So when the parts moved out of the hot zone into the vestibule of the integral quench, the parts would swing back and forth. Well, these parts are hot, and so that they would actually bend, hitting the other parts. So what we did is that we rotated the racking 90 degrees, so these parts would swing back and forth without having to hit another part. This drastically reduced the distortion that was occurring, not due to quench, but due to just the part-to-part interactions during the movement process. Contamination in a polymer quench can cause problems with distortion by not getting the proper quench rate that you expect. Another issue that can do is the temperature at withdrawal. For instance, are you pulling these parts out too hot, or are you pulling them out too cold? If you pull them out too cold, you risk getting cracking. For instance, if I take a bunch of rings, big rolled rings, and I quench them in my polymer and then toss them out in the snow waiting for the furnace to cool down, I'm going to get cracking. Then there's the post-quench operations, and how I handle the parts, the delay before tempering. If I wait too long before tempering, the residual stresses can build in or I can have retained austenite transformed to martensite just because it's colder. And this can contribute to cracking. For instance, for most specifications, you want to allow maximum of 90 minutes before the time you quench to the time you get it into temper. If it's going to be more than 90 minutes, get them in the temper furnace and just do a snap temper, excuse me. You can also do refrigeration, for instance, and that will transform some of the retained austenite to pass the martensite final temperature, final transformation temperature, and this can contribute to distortion or cracking. The tempering, again, this is not as great a factor, but it can contribute to some of the residual stresses by the heat up rate. Again, thicker parts will heat up slower than thinner parts, and the thinner part of the same part will heat up much faster if it's attached to a thicker part. The temperature uniformity, you can see different amounts of transformation on tempering. Again, racking, low density, part-to-part interactions. Finishing operations also contribute to residual stresses. Pickling, plating, all those have a high residual stress associated with it and can cause problems during use and have, for instance, a shortened fatigue life. Grinding, obviously, will make a big difference in terms of the amount of residual stresses, particularly if you show in your Wheaties and really grind it. You can develop quench cracks from the grinding operation or get local soft spots. The prior microstructure can have a big influence on the amount of stresses that you have after heat treatment. For instance, in a study that was done by Art Reardon on two different at the Gleason Works, he took some steels that were an 8620 carburized, roughly 14-inch diameter gears, and he measured the distortion before and after press quenching. Normalized them. He took one, normalized them. The second series was normalized twice, normalized at 1700, then at 1750, and then after press quenching, measured the difference in the amount of distortion out around. And what he saw is that when he double normalized, is that he saw a much more uniform distortion and much less distortion than just a single normalization. And this can be due to better alloy segregation, lower alloy segregation, as well as a much more uniform grain size, which also affects hardenability. In another study by Prinz Hunkel and Hoffman and Hans Werner Zock, they looked at the effect of microstructure on distortion in 5120. And they looked at different types of prior processes, whether it was normalization, annealing, and hardened and tempered prior to hardening. And they looked at the resulting distortion. This is actually from the International Conference on Distortion Engineering in Bremen in 2008. And he noticed that just a single normalization would achieve the largest amount of distortion, and that by progressively refining the grain, either through annealing or hardening and tempering, that they would be able to substantially reduce the distortion occurring. In a study that was conducted by the late Kiyoshi Funatani, he examined the influence of steel hardenability over the ball diameter of a carburized spur gear. And he noticed that the geometry hardenability greatly influenced the change in the overall diameter. Hardenability is a large factor in distortion, and typically the higher the hardenability, the more prone it is going to be for distortion. And in this way, he looked at the hardenability as measured by the geometry end quench test within a given grade of steel. In another study conducted by Dr. Funatani, he looked at the influence of steel hardenability on the pitch area of some hypoid ring gears. And he noticed that as the pitch area, he noticed the pitch area and the maximum pitch area, right, the change in the maximum pitch error increased as the hardenability of the steel increased. Now this is the specific hardness at a given depth on the ring gears. And you notice almost a linear relationship between the hardenability and the pitch error. In another study that was conducted by Stormvinter, Olofsson, Christofferson, and Troll at the Distortion Engineering Conference in Bremen, Germany in 2015, they looked at the effect of different heats on the distortion of specifically the diameter and height of some small cylinders that were 16 millimeters in diameter and 19 millimeters tall. And they saw that as the hardenability increased between the different heats, 3 different heats, that they saw a very large difference in the distortion of these very small diameter cylinders. In the same study that was conducted by Stormvinter and Olofsson, Christofferson, and Troll at IDE 2015, they examined the hardenability of different alloys, the hardenability of different heats within the same alloy group on the amount of crown wheel distortion. And you can see in this that the different heats of material had different responses to the wheel distortion. And you can see that the large variation, while it just averages about the center, you can see that some heats perform differently than the others. For instance, heat J performed in an entirely different fashion than did heat M. Now, some of this work that is done at IDE, the International Distortion, this has been combined with the Quenching Distortion Conference, and it is an excellent resource. I would highly recommend anyone interested in distortion and distortion engineering to attend these conferences. The next conference is in Berlin in April, and it's going to be conducted with the European Heat Treating and Surface Engineering Conference. It's a very excellent series, and I really recommend people attending. I'm going to try if we can get out of this pandemic thing. Machining operations also have an influence on the distortion of the part, after heat treatment. For instance, what's happened is that I'm creating a residual stress at the surface depending upon the condition of my tool. If I have a sharp tool, I will have much better surface conditions. If my part becomes dull, is that I will create more cold work on the surface. This creates more residual stresses at the part, which increases my distortion. For instance, when I'm looking at my cutting depth, the influence of cutting depth strongly influences the amount of overball diameter on distortion. Because as I increase that depth of cut, the error goes up almost exponentially. Even how I grip the part, for instance, during a turning operation, can have an influence on the amount of distortion that I'm seeing on my part. For instance, if I look at the difference between a mandrel and a segment jaws in holding the part during turning, using good cutting practice, this makes a big difference in the amount of distortion that I'm seeing in my part. And in fact, you can see where the segmented jaws, where it's gripped at 3 locations, can have a big influence on the amount of tangential residual stress in the part. This is from a study done by Noag, Salter, Walter, and Bringsmeer at, again, the International Distortion Engineering Conference in Bremen in 2005. The way I hold the part makes a difference in the amount of residual stresses. Now, The amount of stresses is not huge, it's 700 MPa, but this is still pretty significant and can change the shape of the part. In another study looking at holding a part during turning operations, whether it was a pendulum jaws, hard jaws, form locking jaws, they observed different amount of outer roundness after machining just from the different type of holding operation. This outer roundness is a function of the residual stresses that are present. The machining practices also play a part in the amount of residual stresses that are present in a steel. In a very simple DOE that was done by, again, Noack, Zolter, Walter, and Brinksmeer, presented at ID Bremen in 2005, it showed that the high feed rates with a tight nose radius and with different depths of cut and fast cutting speeds all contributed to the differences in residual stresses. For instance, very high cutting speeds contribute to very high residual stresses, whereas low cutting speeds did not. Low feed rates and a low nose radius, and nose radius being the how sharp the tool was. Right? When it's very sharp, you created much lower residual stresses than when your tool is dull. Much higher depth of cuts contributed much higher tangential residual stresses, verifying the results of Funitani that I presented earlier. So that the machining practice can also play a big part in the amount of distortion and residual stresses that during heat treatment will be relieved and distort my part. In another study of machining wrought aluminum parts, presented at another IDE conference in Bremen, you can see that there's differences in cutting speed play a difference in the amount of residual stresses that occur from the maximum for instance, as my cutting speed increases, I increase the residual stress. As I increase the feed per tooth, for instance, when I'm machining a gear, that it makes a big difference in terms of the residual stresses that are going to be present. Now we start talking about heat treating, and specifically carburizing. In a study that was done by ZF, by Bonson, Clausen, Hoffman, Mayer, and Hans-Werner Zock, on the influence of carburizing on distortion behavior, that was also presented in Bremen. They looked at different variables on the change in the curvature of a part as well as the diameter of the part. They looked at carburizing depth, the process sequence, surface carbon content, and carburizing temperature. They saw that the biggest effect in terms of cause of curvature was the carburizing depth, with very little effect on surface carbon content. Now, in terms of changes in diameter, the carburizing depth again showed the greatest effect, followed by the carburizing temperature. The surface carbon content showed the least effect. Again, when looking at carburizing, they were looking at the effect of temperature for carburizing and its effect on distortion. And in this case, that they found that there were minor differences between one face and the opposite face due to different carburizing temperatures on a small clutch part, on a heavy-duty clutch. But the carburizing temperature made a big difference in terms of the distortion on one face and the other as my temperature of carburizing increased. In the same study, they examined the gear teeth and its performance, and they looked at that as a function of carburizing temperature. And they noticed in this case, that there was an effective carburizing temperature for just the inner bore diameter and to some small extent the outer diameter. there was very little effect on radial runout of the gear teeth. This is interesting, and it shows that there is pretty much an optimum carburizing temperature for this particular part in this particular quenching operation. In a study that was conducted by Chitani looking at different types of Japanese oils that were present, that showed that the oil type had a big effect on, one, the hardness, as well as the type of cylindrical or elliptical distortion that you're going to see. As a general rule, the faster you quenched, the greater the distortion. You also see greater hardness too. The oil temperature for these different operations showed drastic improvements as I increased the oil temperature. As I go from 60 degrees C, or roughly 140 degrees Fahrenheit, to 200 degrees C, or about 350 degrees Fahrenheit, that I could show the cylindrical distortion decreased dramatically, and dramatically decreased the elliptical distortion. Now, what was interesting, at approximately 100 degrees C, that I did see an increase in the elliptical distortion, and I'm not quite sure why. But just in general, is that the oil type and the oil temperature play a drastic influence on the amount of residual stress and the distortion that you will see in your part. Different types of quenchants can influence the distortion that you're going to see. Depending on the agitation and depending upon the part or the tempering that you're going to see. Is it, for instance, the cold oils? In this study, it showed that the agitated part showed greater distortion than no agitation. And this could be due to not so much agitation as the non-uniformity of heat transfer around the surface of the part. For more tempering oil, it showed that agitation improved it. Again, the paper that this was pulled from did not indicate how these parts were racked and what sort of distortion or velocity was achieved between the two. So that it's not really clear, but what it's showing is that agitation can have an influence on my part. And it's showing that the different types of quenching can influence the distortion in the part, whether it is a cold oil, more tempering oil, or a salt. Contamination of a quenchant can also cause problems with distortion. It can cause problems with also achieving properties. In this case, we were examining the effect of hydraulic oil contamination on the cooling curve of an oil quenchant. It's not uncommon for, particularly in hydraulically operated quench presses, to have a hydraulic oil contamination. Hydraulic oils are base straight mineral oils with very few additives, so that as I increase my hydraulic oil content, typically my quench speed will decrease. This quench speed can influence the amount of hardness as well as the amount of distortion that I can see. As you can see, it changes the viscosity and the flash point of the oil. The way I rack a part or I fixture a part can influence the amount of distortion that is present on the part. For instance, if I have, for instance, in this case it was a disc, and I'm supporting it by either two locations or by a central ring, and I'm supporting it completely around, can influence the amount of distortion that I'm seeing. For instance, in the figure to the right, if I have two-point loading, that I start seeing a great deal of distortion occurring, much greater than completely supporting it around the entire periphery of the part. The amount of oil canning or warping that I see on the left is also dependent on the amount of support that I'm seeing. If I just support it at two locations, right, that I can potentially have sagging in between of the part. If I have a 3-point loading where I'm supporting it around around the circumference of the part, I see much lower distortion. One thing that happens in the heat treat shop is that I use my grids over and over and over again. As I use these grids, the flatness on these parts will change. And so any of the jigs or fixtures that I'm using will change the more I use them. And it's showing that the distortion increases in a study that was done by Takahashi and Toyota, that the distortion measured by flatness of some more-tempered gear, carburized and more-tempered gear, will change as a function of the flatness of my base jig or my base grid. Is that there is a certain life that I see before my distortion starts increasing. And so this tells me of how often I have to change out my grids before I start seeing excessive distortion. Again, the racking and fixturing plays an important part on how the part is quenched and the resultant residual stresses. For racking or fixturing a part, the method in which the part enters the quench can play a big difference in terms of the resultant distortion. Here was a study that was done at Toyota on some gear teeth that were quenched in different orientations. And they saw when they quenched it sideways, they saw much less distortion on the lead face than the coaster face. And they saw much less variation. When they put the gear in face going in vertically, that they got reduced lead and pitch error between the two parts. Now, just one thing that's just really should be taken, you've made a tremendous investment in the quenchant that you've picked, whoever vendor you're using. And for most oil quenchants, you should always test and make sure that you're getting consistent quenching. And this is by doing a cooling curve. You also want to look at the safety issues. For instance, flash point in water. Make sure my flash point maintains a high and I don't have any water. I also want to start looking at the cleanliness of my oil by looking at my sludge, precipitation number, and total acid number, because these affect the cleanliness of my part. So I have three things that I'm looking at. I'm looking at a safety aspect, I'm looking at a cleanliness aspect, and I'm looking for my quench capability. And the idea of doing routine testing, typically once a quarter is adequate, is to catch problems and to determine corrective actions to be taken. And it's really the customer and supplier working together. The idea is to protect your investment in your quenchant. In this short talk, we've talked about some of the key influences on controlling distortion and residual stresses. The big effects are machining, how this part is made into near net shape, the hardenability of the steel, the quenchant that's chosen and how you quench, as well as how these parts literally enter the quenchant, how these parts are fixtured, how these parts are racked, can have a drastic influence on the amount of distortion and residual stresses that you'll see on your part. These four main topics, machining, hardenability, quenching, and racking and fixturing, are the big sources of distortion and residual stress. And I wanted to thank you. And are there any questions?